Alright, here we are at lesson 3.4, and this topic, I believe, is probably the most challenging one that you will have faced so far in this course. I remember people in pre-calculus telling me, oh, I hate word problems, I hate word problems. Well, guess what we're doing today? That's right, story problems. And in this type of scenario, the idea is we want to find the rate of change. And all of these rates of changes are with respect to time. And you're thinking, rate of change, isn't that the derivative? But it's the rate of change of one quantity by using the rate of change, and also with respect to time, of a related quantity. That's why we call this related rates. So if you think about what I mean by with respect to time, remember when I had a question like this, y equals x squared, and we found the derivative, that was 2x. Well, this was with respect to x, right? So that's why sometimes you saw this notation, d dx of x squared. Or you saw this notation for y prime, dy dx. However, now what I'm saying is, we're not using x. So forget d dx, it's d dt. Okay, and therefore this is not dy dx, it's dy dt, because I'm trying to find rates of change with respect to time. So really now, if I were to do this same question, okay, y equals to x squared, I want you to realize that y is a function of t, and x is also a function of t. So when I ask you to find y prime, or the derivative, it's now really take the derivative of y like this, take the derivative of x squared like this, because t is my independent variable, and therefore this actually can be written as dy dt. And this on the right hand side can be written as, well, it's the derivative, which is 2x, and then now chain rule, because x is a function of t. Yes, you heard me right, chain rule, or yes, this is like implicit differentiation, dx dt. Okay, so that's a little bit of a preview of what you're going to be doing. Now, we can go through this procedure, but I prefer to actually go through some examples, and then you can come back and look at this procedure. If you like kind of recipes, this is what you can do. The key thing I think I want us to realize is when you write an equation relating to variables, if a quantity is changing, it must be represented with a variable. Okay, quantity changing has to be a variable. If it's a constant, however, then we should represent it with a number. Okay, and this last part here, sometimes this comes in handy when you can look for secondary relationships between quantities. Sometimes you're going to have like 3 or 4 variables in this equation. That's way too many for us. So look for a secondary relationship that helps us minimize the number of variables, hopefully to perhaps 2 or maybe 3 at most. Okay, and then the key thing then, once you've done all that, is to implicitly differentiate both sides, the stuff we learned last day. Some formulas that might come in handy as you talk about related rates. If you think about something like the right angle triangle formula, if I wanted to relate these side lengths, I can use this equation to relate all 3 side lengths, right? A squared plus b squared c squared. So just some other ones that you hopefully learned in your pre-calculus studies. Just be aware of them and be able to use them. All right? So we're going to start off relatively straightforward with procedure first, and then we'll get to a word problem. Okay? So in number 1, we actually did what they call the first 3 steps of the procedures. So they actually drew a figure or figured out the unknowns. They wrote down what was given, and then they now are asking you to find dy dt. So here's all this information they got. The rate of change of x with respect to t is -6. Y, the y variable itself, is 4 at some moment in time. Okay? And what they also told you was that the relationship between the 2 variables, x and y, is equal to 12. So knowing this relationship, right, this is the relationship or the related rate, right, related equation. Your goal here is to find dy dt, one of the rates of change. So how would you do this? Well, the question is, can you figure out the derivative of xy equals to 12 implicitly? And if you remember, x times y, or a and b, a prime. So what's a prime here? That would be the derivative of x. So I'm going to write this as dx dt, because everything is in terms of time now. Dx dt. So a prime b plus b prime. Now what's b prime again? That's the derivative of y. So that's dy dt. B prime a, and the derivative of 12 is 0. Okay. Now that you have this, you're like 4 different variables. You're trying to find dy dt. So you should be able to plug in everything else. So dx dt, that's negative 6. Y, that's 4. Dy dt, that's what I want to figure out. And what is x? Well, they don't actually tell you what x is. But can you figure it out? So remember, this is the scenario, right? This is what's happening at this moment in time. At the moment when y equals to 4, we have dx dt equals negative 6. But at the moment when y equals to 4, we should be also able to figure out what x is, because x times y equals to 12. And so if you said when y equals to 4 also implies that x equals to 3, that is correct. And now you can replace x with 3. And then go ahead and solve. So 3 dy dt equals to 24. So dy dt just equals number 8. Okay? So this was a simplified form because I gave you all the information and I gave you the equations. Most likely they're not like that, like in example number 2. So in example number 2, I want you to read the question. I want you to analyze this diagram, and then I want you to actually figure out what information is given and actually list that out first. And then finally, can you find an equation that relates all the variables? Okay? It's a lot of work, I know, but we'll do this together. So a windlass is used to tow a boat to a dock. That's something here, right? Towing this rope. The rope is attached to the boat at a point 15 feet below the windlass. And if the windlass pulls in the rope at a rate, okay, so hint, 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 when I see this word rate, I'm thinking derivative, at a rate of 30 feet per minute, at what rate, asking for another rate now, at what rate is the boat approaching the dock when there is 25 feet of rope out? Wow. Okay, so draw figures, procedure number 1, and I've done that for you already. Pretty boat. Now is this horizontal distance. This 15 is always the same because it says it's always 15 feet below the windlass. And you have this diagonal which represents the length of the rope. Okay, so let's see what kind of information do we have. So let's read this again. If the windlass pulls in the rope at a rate of 30 feet per minute. So this is some sort of rate. Is it a rate of the z variable or the x variable here? It's pulling in the rope, so if you said dz dt equals to 30 feet ft, feet per minute, I'd say you are almost correct. Almost, because of this key word. In. It's pulling it in. It's pulling it towards. So is the length of z increasing or decreasing? Yes, it is decreasing, so it should be negative 30. Okay, now this is the rate, and it says at what rate is the boat approaching the dock. So what is this looking at in terms of my variables? The rate the boat is approaching the dock is dx dt. So I want to find out dx dt. I want to figure out what that is. But when? Right? And what scenario? Because it changes all the time depending on how long the rope is and how fast you're pulling it in. So it's saying at what rate is this boat approaching when there is 25 feet of rope out. So what is dx dt when there is 25 feet of rope? When z equals to 25. That's what they want you to find out. So we've done step 1 of the procedure, drawing a figure. We've done step 2 now, write what is given. And now you need to find an equation relating the variables. So what lovely equation relates all of these variables? You guessed it, Pythagoras to the rescue. X squared plus 15 squared equals to z squared. Great. And now we need to figure out what? Well, we need to implicitly differentiate. So let's go ahead and implicitly differentiate with respect to t. So now I'm just going to say next step is to differentiate with respect to t. And so the derivative of x squared is 2x times dx dt. The derivative of 15 squared is 0. Good. And the derivative of z squared is 2z dz dt. And so now we should just plug in the numbers and solve. So what do we have here? We have here dz dt. We know that is equal to negative 30. So that's negative 30. We know z in this case is 25. We know... do we know what x is? Well, we kind of do. It says when z equals 25. So when z equals 25, what does the actual picture look like at that moment in time? Well, here we go. Here's your right angle triangle, and you can solve for x in this case. So x squared plus 15 squared equals to 25 squared. I'll tell you that x must be 20. So at this moment in time, when I said z equals to 25, it also implies that x equals to 20. And let me put that here, and now I should be able to solve for dx dt. There's 2's on both sides. I'll just divide them out. And so dx dt equals to 25 times negative 30, all divided by 20. And that, my friends, I believe is negative 37.5. Now, be careful here. Units matter. This is a rate. So this is talking about feet per what? Remember, it's in respect to time, so feet per minute. So in this case, I'm going to write a little blurb, and I'm going to say something like this. When the rope is 25 feet long, the boat's distance, and I'll say from the dock, and I'll also say this, is, and I'll reference that negative to this word, is decreasing at a rate of 37.5 feet per minute. There you go. And that's what I mean by writing a sentence explaining the meaning of the answer. Okay? Wow. Okay, so here is your first example of a related rate question. I've got 2 more on the next page, so let's work on those. I'm going to ask you to try number 3 on your own first, please. So read it, find the information, find the relationship between all the variables, implicitly differentiate, plug it in, and solve. Whew, lots of stuff. Okay? So I'm going to ask you to try that yourself first, so pause my video right now, and then come back when you're done. Please, please, please don't cheat. Come back when you're done. Or come back when you're stuck. Okay? Okay, so let's see. A policeman traveling south toward an intersection. So someone's traveling south, spots a speeding car traveling east away from the intersection. Zoom. When the policeman is 0.6 miles from the intersection, the car is 0.8 miles from the intersection. And the police's radar shows that the distance between them is increasing at a rate of 20 miles per hour. Wow. Okay, that's a lot of stuff. I think we need to look at a third variable here too. So I'm thinking y variable, x variable, z variable, the distance between them. Okay, so when the policeman is 0.6 miles from the intersection, so I'm thinking that looks like the y value is equal to 0.6. And the car is 0.8 miles from the intersection. I think x would be 0.8 or 0.08. It says the policeman's radar shows the distance between them. The distance between them is increasing at a rate of 20 miles per hour. So I'm thinking that's rate. That must be a derivative. And it's the distance between them, which is z. So I know that dz dt must be increasing, so it's positive 20 miles per hour. Okay? Now it says, if the speed of the police car is 60, that must be dy dt. Okay? What is the speed of the car? I'm asking you to find dx dt. Okay? Now I did leave out something quite important here. I'd like you to refer back to dy dt. I said this is 60 miles per hour, which means this is increasing. It's getting away. But if you look at my diagram, the police car is traveling towards the intersection point. So really, because it's traveling towards, that y value is shrinking. And because that y value is shrinking, yes, you need to put a negative. Okay? Alright, draw my diagram, label my variables. Next step, find the equation that relates all these things. So if you thought, oh, it's Pythagoras again, you are correct. This time, however, all three of these variables, x, y, and z, are variables. Nothing is constant, so I can't replace it with a number. So now when I take the derivative, it's 2x times dx dt. This is doing it implicitly. 2y times dy dt, and then finally 2z times dz dt. Okay? Notice in this case those 2's appear everywhere, so I'm just going to divide them all out. And now I'm just going to replace the numbers. So here we go. X is 0.8. Dx dt is something we want to figure out. Y is 0.6. Dy dt is negative 60. Z. Uh-oh, I don't have z. I have x and y. But that will help me figure out z. If this is 0.6, this is 0.8. Hopefully you know this is 1.0 using Pythagoras. I'm not going to show you that, but I hope you do know and can find it yourself. If you can't, ask a friend or just plug it into this equation. And dz dt we found was 20 miles per hour. Doing all these calculations, what do we see then? I think that's 20 minus that. I think that's 56 on the right hand side. We still have here 0.8 dx dt on the left hand side. We'll divide by 0.8, which I believe gives us 70, and our units are once again miles per hour. And as a sentence, I'll say the car is moving. And because it's positive, I'll say moving away, not towards, away from the intersection at the speed of 70 miles per hour, mph. Okay? Alright. I'm hoping you're getting the hang of this. Like I said, I think this is the most difficult thing you've done so far in this course. But nonetheless, if you are getting the hang of this, bravo. And if you're not, don't worry. It's hard. It's hard. Don't worry. Just keep on trying. Keep on working through it. And the more you do, I think, the more you'll get better at it. Alright, last example here today. Ooh, gravel. It's falling onto a conical pile at a rate of 10 feet cubed per minute. By the way, sometimes looking at the units of a rate will help you determine what you're trying to define that as. It says at all times the radius of a cone is twice the height of the cone. The radius is twice the height. Okay. And then it says find the rate of change of the height when the radius is 6 feet. And you're so fortunate. The formula describing or relating all of these variables has been given to you. Oh, Christmas has come early. V, volume, is equal to 1/3 pi r squared h. Okay, so we know there's some sort of volume, and I would have known that too because I see this feet cubed, right? So that must represent dv dt, the rate of change of volume, must be 10. Okay. It says at all times the radius of the cone is twice the height. So if you think about that, the radius, r, is always twice the height. R equals to 2h. This is interesting. This is like that secondary relationship. Secondary relationship. Okay. That will help us perhaps eliminate all these extra variables. Okay. What else do we have here? It says find the rate of change when the radius of the pile is 6 feet. So find the rate of change of the height. So find dh dt. Okay, I want you to figure out that when r equals to 6. And remember, r equals to 6, which also should imply that this also implies that h equals to, because r equals double of h, or 2 h's, h must be 3. Okay? Alright, so that's all the information we know, and now the question is, let's go ahead and do this implicit differentiation. Now, you might be thinking, oh, I see this as a constant. Great. By the way, don't write this down. Just watch. And then, I see two things multiplied together. A prime B. I know you love singing this song a lot, but maybe there's an easier way of doing this one. By all means, if you want to do it this way, go right ahead and do product rule, and you'll get the same answer in the end. However, most people would rather eliminate one of the variables and just have one left to work on. And that's where that secondary relationship comes in to play, because r equals to 2h, so I can replace r with 2h, and then I'll square that with an h, and I'll make that my new equation with v. 1/3 pi 2h squared is 4h squared times h. That must be 4h squared h, where I can write volume as 4/3 pi h cubed. And now this might be helpful because there is only one variable on the right hand side now, just like the other questions we did. Maybe now it's a little bit easier to deal with. And now at this moment, now we can differentiate. Once again with respect to t, because t is our independent variable here, or time. And let's see what we get. So v prime can be written as dv dt. 4/3 pi is a constant, and now I'm going to take the derivative of h cubed, which is 3h squared. And don't forget, yes, implicit differentiation, dh dt. Those 3's are nice. One's in the denominator, one's in the numerator. Goodbye. I'm going to now substitute in the values. dv dt, yes, is 10. 4 pi. H, oh yes, that's 3, so 3 squared. And now we're left with just dh dt. Beautiful. And if I wanted to solve for dh dt exactly, I'll just take 10 and I'll divide that by, what's this? 3 squared is 9. 9 times 4 is 36, so this will be 36 pi. Or if you want me to simplify, that's equivalent to 5/18 pi. And our units here, please. Yeah, feet per minute. And as a sentence to finish us off, I'll say when the radius is 6 feet, the height of the pile is, and once again because it's positive, oops, once again because it's positive, the height of the pile is increasing at a rate of 5/18 pi. Be careful here, make sure the pi is in the denominator. Feet per minute. Woo! Alright, I know this is heavy duty, but you need to practice. So get started on assignment 3.4 and ask questions if you don't understand.